Hello friends, good morning to all of you. In previous lectures we have to discussed about the definition of the groups, subgroups, normal subgroups, and in today's lecture we will discuss about homomorphism of groups. That means we have to apply the mapping between the two groups. Homomorphism of groups. Let G and G dash are any two groups with binary operations star and star dash respectively. Then the mapping phi from G to G dash is called homomorphism if phi of x star y is equal to phi of x star dash phi of y for every x y belongs to G. That is the mapping phi preserve the group operations all the operations of G and G dash are quite different. Special cases of homomorphism we are discussing some special cases of the homomorphism. That means the mapping is homomorphism and satisfy one or more conditions, then they are called different types of the homomorphism. First, monomorphism. Let phi is homomorphism between the groups G and G dash, then phi is called monomorphism if phi is 1-1 mapping also. Second, epimorphism. phi is a homomorphism between the groups G and G dash if the mapping phi is onto mapping then it is called epimorphism. Isomorphism. The homomorphism phi from G to G dash is called an isomorphism if phi is 1 and onto mapping. Let G and G dash are any two groups and phi is isomorphism from G to G dash, that is phi is homomorphism phi is 1 and onto, then G dash is called isomorphic image of G. We can write it as G is isomorphic to G dash. Now the next endomorphism. Let G be any group and phi is homomorphism from G to G into G dash, G into G itself, then this mapping phi is called endomorphism. That means the homomorphism from G into itself. In this case, we replace G dash by G itself. Then this mapping is called endomorphism. Next, automorphism. Let G be any group and phi is homomorphism from G onto G itself. Then phi is called automorphism on G. Next, kernel of the mapping phi. Let phi is homomorphism from the group G to G dash. Then kernel of phi is defined as kernel of phi is equal to x belongs to G such that phi of x is equal to identity of G dash. That means kernel of phi is the subset of G. The elements in kernel of phi which image under phi is identity element of G dash. Next, image of phi. Let G and G dash are any two groups. Phi is a mapping from G to G dash. Then image of phi, image of G under phi is denoted by phi of G and defined as phi of G is equal to phi of x such that x is belongs to G. Now we will discuss some examples of homomorphism. Show that phi z2 z by z2 defined by phi of m is equal to m plus z2 is a homomorphism. Determine its kernel. Solution. It is given that phi is a mapping from Z to Z by Z2. Let Z be the group of integers with binary operation addition and Z2 is also a group of multiple of 2 of integers with respect to addition, that is Z is equal to x such that x is an integer, Z2 is equal to y such that y is equal to 2x, x is belongs to z. Then z2 is normal subgroup of z. Therefore z by z2 is defined because z2 is normal subgroup of z, then z divided by z2 is called the quotient group. Z by z2 is equal to x plus z2 such that x is belongs to capital Z. We have to prove that phi is homomorphism. Let x y belongs to z. Consider phi of x plus y is equal to phi x plus y plus z2 because by definition of phi we can write it as x plus z2 plus y plus z2, which is equal to phi of x plus phi of y. This implies phi of x plus y is equal to phi of x plus phi of y. So phi is homomorphism. Find the kernel of phi. Kernel of phi is equal to x belongs to G such that phi of x is equal to identity of z by z2. That is, x belongs to z such that phi of x is equal to z2, because identity of z by z2 is z2, which is equal to x belongs to z such that x plus z2 is equal to z2, because phi of x is equal to x plus z2, which is equal to x belongs to z such that x is belongs to z2. This implies kernel of phi is equal to z2. The more examples of homomorphisms and theorems we will discuss in the next lecture. So keep in touch, watch our videos, subscribe our channel. Thanks to all. Have a nice day. Bye bye.